So we're going to be doing further pure 2 today, and yeah, let's start off with hyperbolic functions. Okay, so in this video you're going to be learning how to use hyperbolic functions. So basically you're going to learn the what. Okay, you're going to learn the identities. You're going to learn the calculus behind it, and maybe a few miscellaneous examples as well included in this. Okay, so this is what we're going to be doing all throughout. Now let's start off with what hyperbolic functions are. Well, we have the regular sine, cos, tan, and their reciprocals, which is cosec, sec, and cot. Okay, so this is just the reciprocals of it. Now when you introduce a hyperbolic functions, you simply put an h next to it. So sine h, cos h, tan h, cosec h, sec h, and cot h. Now we pronounce this as sine, cos, tan, cosec, sech, and cot. But yeah, we don't need to, they don't test pronunciations during the exam, so that's relief. But what isn't relief is how they're really tricky. Okay, so firstly you should know that sine h, okay, I'm going to call this sine h, okay, in case this is a bit confusing, is e to the power of x minus e to the power of negative x over 2. This is what sine h looks like. Okay, so it's really easy. Now if you were to plot a graph, okay, let's say that you were to plot a graph, okay, of the function of sine h, okay, you could just plug in x equals 1 2 3 and go on, but I'm going to save you that time. It's going to look something like this. It's going to look something like this and goes on like that. Okay, so yeah, that's how it's going to look like. And yeah, that's just it. So if you drew y equals e to the power of x, it would follow it would follow that kind of a trajectory here. And if you drew y equals e to the power of x, and if you drew y equals e to the power of negative x, you would get something along this. Okay, this is y equals to e to the power of, sorry, it'll be negative e to the power of negative x. Okay, yeah. So basically if you just took the averages, okay, so basically we just sum up e to the power of x with negative e to the power of negative x, and then we divide them by 2. In doing so, what we've just done is basically just found the average between each value. So if we took a value over here, we found the midpoint of that value, you'll get a sine h point. That's what we're going to do. Okay, so that's how sine h works. Now the next identity that we're going to be doing is going to be cos. So now we're gonna look for cos x. Okay, for cos now it works pretty much the same as sine, except instead of minus we put a plus here, and e to the power of minus x over 2. Okay, so pretty much the same as cos as sine as well. So yeah, this is what we're going to be having. And if we were to plot a graph over there, just like that, okay, if we were to plot this kind of graph, we would be getting something like this, like a big U, like that, something like that. Okay, and yeah, now you can plot in y equals e to the power of negative x. Okay, if you did this, you would be getting something like this. Okay, and if you did y equals e to the power of x, you'll be getting something like this, basically the exact opposite of it. Okay, and this is y equals e to the power of x. Now you should know that when you're summing up e to the power of x and e to the power of negative x, and you divide by 2, you're basically summing up two values and finding the midpoint of the values, basically that mean value. So taking a value over here and a value over here, finding the average of this will give you a function of cos h. Okay, so it's simply the averages of a particular value of e to the power x and e to the power negative x. Okay, now that's how I view trigonometric identities, like hyperbolic functions. Okay, now moving on, we got tanh x. Okay, Now we know that sine over cos gives you tan, and the same way it doesn't change here. Sine over cos equals to tan. So in doing so, we'd be getting e to the power of x minus e to the power of negative x by 2, and we have to divide this by e to the power of x plus e to the power of negative x whole divided by 2. Now if we did a bit of math, which isn't really that much, we'd be getting this right here. Okay, so yeah, this is the function you're going to be getting. It's a weird combination of exponentials. I would suggest not to by heart it, but just to remember sin x and cos x, and then you find for every other one. So this is what tan is going to look like. Okay, now if you were to plot a graph of that, okay, let's plot a graph for that. Okay, so for tan x, plotting a graph for tan x is actually kind of simple. They do have a range though. Okay, so let's call this range, and this is the other range. So yeah, tan x looks a bit weird. It's actually like this, like that, and then it goes asymptotes to that. Okay, where this is y equals to 1, y equals to minus 1. So the range of tan x is between 1 and minus 1, and that's how tan x is going to look like. So yeah, it's pretty much simple. You really shouldn't take too much concern in it. I would suggest that you remember how to draw these graphs, because until now it's not been tested in the new syllabus. But if I know CIE at all, they're probably going to ask you some sort of question regarding drawing hyperbolics. Don't take my word for it, but it's best that you know. So yeah, moving on. Okay, so that's well done. Now moving on, we gotta do sech. Okay, now we can tackle cosec actually. Let's tackle cosec. So we know that 1 over sine gives you cosec. So in that same way, you can say 1 over sine equals to cosec. And yeah, in doing so, you'd be getting cosec equals to 2 over e to the power of x minus e to the power of negative x. And that's it. That's cosec for you. Cosec x. Okay, now you can forget about the x part. Okay, but yeah, this is how it's going to look like. Now if you were to plot this on a graph, as usual, I'm going to look at the graphs obviously. If you were to plot this cosec, you're going to get something along the lines of this here. Okay, that's how it's going to look like. Yeah, and you should know that if you plotted f of x equals to cosec x, f of x can never ever equal to 0. It cannot. Okay, there's an asymptote right over there. And yeah, that's pretty much it. Now you also have a restriction on the domain. You can't put x equals to 0, because then this would be it will be 2 divided by 1 minus 1, and that is 2 over 0. So yeah, that is a restriction on the domain, because it's just not possible. Okay, moving on, we have to tackle on sech x. Now this, using the previous identities, you can say 1 over cos equals to sech x, and in doing so you'd be getting 2 over e to the power of x plus e to the power of minus x. This is what sech x is going to look like. Now plotting that on a graph would look something like this. So this peaks over here right there, and then it goes back down like that. Okay, it's supposed to be a bit smoother, doesn't need to be that high of a peak, but this peak is at y equals to 1. Okay, and yeah, the range is between 0 to 1. Okay, that's the range of the values over here. Yeah, that's only if you put f of x equals to sech x. And yeah, that's the range. So now we have the final trigonometric identity that we need to tackle, and that's none other than cot. x. So this is just 1 over tan. It's 1 over tan, which is the same as cos over sine. So if we looked at it carefully, you'd be getting e to the power of x plus e to the power of minus x whole over e to the power of x minus e to the power of negative x. Okay, now that's 1 over tan, by the way. We plot this. Okay, yeah, so we plot this on a graph. Based on that, it would be something like this and something like this. Okay, and in this case we have a few asymptotes here. This is one asymptote and this is the other asymptote. Y equals 1 is an asymptote, y equals to minus 1 is another asymptote. Sorry, x equals to minus 1. Wait, no, this is, wait, I'm a bit confused. Yeah, wait, the range, you don't need to write down this. Yeah, y equals to minus 1 and y equals to 1, they are the two different ranges. But yeah, if you plotted this, it would be somewhere, basically it would always be lower than negative 1, or it's going to be f of x is going to be greater than 1. Okay, that's always the case whenever you have f of x equals to cot x. Forgive the handwriting, but yeah, that's just how it's going to be. So yeah, that was pretty much the fundamental of all the trigonometric functions. Now the second step, identities. Okay, firstly I just want you to know sin x plus cos x. Okay, we do this, we get e to the power of x minus e to the power of minus x divided by 2 plus e to the power of x plus e to the power of minus x divided by 2. Now we simplify this, and we would be getting 2e to the power of x divided by 2, which is equal to e to the power of x. So a tiny identity to remember, sin x plus cos x equals to e to the power of x. It's a very good identity to remember, and yeah, it's gonna be in handy sometimes. So yeah, okay, back at it. Now let's focus on a few identities over here. Okay, now normally you have the double angle and compound angle formulas, and yeah, we're going to tackle exactly those. Now there is a small condition. Okay, you should remember that the trig identities equals to the hyperbolic identities, is equal to the hyperbolic identities. Okay, in all cases, but with a twist. Whenever you multiply a sine times sine, there is a sign change. Okay, there is sign change. Basically means that you have to multiply by negative 1. Multiply by negative 1. Now what does this even mean, you may ask? Well, let's understand this from a different perspective. Okay, we know that cos squared theta plus sine squared theta equals to 1. So if trig identities were equal to hyperbolic identities, we'd be getting cos squared theta plus sine squared theta equals to 1, correct? Well, no, this is wrong, because over here you can see sin x, this term right here is actually sin theta multiplied by sin theta, and whenever you multiply two sin thetas, you have to multiply by a negative 1 as well for an identity. Okay, this is only for an identity, never multiply by negative 1 generally. You multiply by negative 1 only to prove an identity. Okay, so we have to multiply this by negative 1. So actually our result becomes cos squared theta minus sin squared theta equals to 1. So yeah, that's how a function is going to look like. If you have sin x over cos x, this remains to be tan x, because you're not multiplying sin x with any other sin x. If you do sin x times sin y, you'll be getting well, you'd have to do a negative. Okay, you have to bring in the negative now, and you write your function. Okay, it's really important that you guys know this. Now, erasing all ink. That was for the first identity. So yeah, identity to note cos squared x minus sin squared x and x equals to 1. Okay, now our next identity that we can go with 1 plus tan squared theta equals to secant squared theta. Okay, now let's evaluate this. Let's just take this side for once. 1 plus, now tan squared theta is, well, let's write this in terms of hyperbolics first. Tan squared theta equals to sec squared theta. Now evaluating tan squared theta, that would be 1 over 1 plus sin squared theta over cos squared theta. Okay, and we know that whenever we multiply two sines, it's actually going to be a minus. So now we have 1 minus, it's going to turn into 1 minus sin squared theta over cos squared theta. Okay, now we know this right here is tan squared theta, so now our identity is changed. 1 minus tan squared theta equals to sec squared theta, and this is the identity, the second identity. Not all the identities are given in the list of formulae MF19. Yeah, most of them are given, but there are a few that aren't given, so you have to be aware of the formulas. It's really important you know how to use the identities. Okay, now moving on. Let's see, is this on the slide? Okay, yeah, so we could do this for each and every trigonometric identity you want. I just think that's going to be a waste of time, so we don't need to do that. Let's move on to some compound angle formulae, okay, because that's where people are going to find it a bit tricky. Okay, so we know that well, for sine a plus b, a plus or minus b, we got sine a cos b, whoops, sine a cos b plus sine b cos a. Okay, but the thing is, we don't if we replaced every sine with sine and every cos with cos, then there's no change. There's still no change to it. Whoopsies. Yeah, there's no change to the entire thing. Okay, regardless, the same thing applies for cos. Okay, we could use cos a plus or minus b. We'll be getting cos a cos b, or cos a cos b, plus or minus or plus sin a cos b. So in doing that, we'd be getting tan. So if we did tan, okay, now tan a plus or minus b. Okay, we do this according to the formula. We should be getting tan a plus or minus tan b whole divided by 1 minus or plus tan a times tan b. Okay, so according to the formula, this is how our formula for tan a plus or minus b looks like. Now over here there is one tiny modification. I told you every trig equals to a hyperbolic identity. Okay, every trigonometric identity applies to a hyperbolic identity, except whenever we multiply sin x times sin x, or sin x times sin y. In this case we have sin a times sin b. Okay, let's just evaluate the denominator real quick, specifically this term. Okay, we'll be getting sin a times sin b divided by cos a cos b. times that. Okay, and you can see over here we're multiplying two Shine functions, even though the value a and b are different. We're multiplying two Shine functions, therefore we're going to have a minus instead. So this minus or plus actually turns into plus or minus over here. So we have our new identity, and that's tanh of a plus or minus b. A plus or minus b equals to so using the identities, we can do tanh a plus or minus tanh b whole divided by 1 plus or minus tanh a tanh b. And that's how we use the compound angle formula. Okay, it remains the same for all the other ones as well. And yeah, using compound angle you can find your double angle as well. Even though that's unnecessary, I'm gonna still do it so that it can be of greater help. Now let's erase this real quick. Okay, yeah, now for double angle, we know sine 2a in the formula booklet. Sine 2a equals to sine a times cos a. Now we can replace that of sine 2a equals to 2 sine a times cos a. Okay, so that doesn't change, it remains exactly the same, no changes in there. Now for cos 2a equals to cos squared a minus sine squared a. Okay, so we replace this with cos. If you want, you can replace this with cos squared theta or whatever. You'll be getting cos squared theta minus sine squared theta. Okay, so yeah, we'd be getting this plus this, and yeah, this should be the identity normally, but using the identity we had earlier, we should know. Wait, now using the identity that we had earlier, we should know that sine squared theta, that's going to change. Okay, we're still supposed to use a. Yeah, we're going to know that since you're multiplying sine squared 2 times, you're going to actually have a negative over here. So another negative times negative is positive. So we have a new formula, cos 2a equals to cos squared a plus sine squared a. And that's the second double angle formula. The third one, using the compound angle formula that we did earlier, tanh a plus or minus b equals to tanh a plus or minus tanh b over 1 plus or minus tanh a times tanh b. Okay, this is what the formula was. Forgive the handwriting, but I'm pretty sure you guys knew the formula. We can just substitute a equals to b or b equals to a, whatever. We'd be getting tanh 2a. Now this is where the double angle starts. We'd be getting 2 tanh a over 1. Now since it's plus, because it's double angle, we're going to do 1 plus. Okay, that's important. 1 plus tanh a times tanh a. So tanh a the whole squared, and yeah, it'll be tanh squared a, but that's the gist of it. Okay, now that you know the basics of the identities, you're ready to move on with a few more advanced ones. These were simply trig equals to hyperbolics. This is simply trig equals to hyperbolics. Simply just remember sine x times sine y or sine x, it doesn't matter. Whenever you multiply two sines, it gives you you have to multiply by -1. Multiply by -1, that's important. Okay, now moving on, we need to erase this. Okay, now we have a few more identities that you need to learn. This is going to be a little bit more trickier, so it's best that you learn it. So now we have inverse functions. Sine inverse of x. This is the ln of modulus, you have to use modulus, x plus root x squared plus 1. Okay, in this case you don't need modulus because it's in brackets. Yeah, I mean, you don't really need to put, it's not necessary. I would prefer that you put modulus anyways, but yeah, sin inverse of x equals to the ln of this. Okay, now cosh works exactly the same way. Okay, it's literally the same except we have a minus here instead of a plus, so that would look like x plus root x squared minus 1. That's it, that's cosh. Okay, so yeah, that's also another easy one. As for tanh, you could just do, you know, divisions, but don't do that. Preferably we do 1 by 2 times ln of 1 plus x divided by 1 minus x. Okay, now this condition is only if the modulus of x is lower than 1. Okay, basically it means the magnitude of x, it must be lower than 1. The reason being so is because, well, this cannot be negative, otherwise it invalidates it, but I guess that's why you have the modulus here. So yeah, remember these identities. These are the best use of identities here, because now they're going to ask you a lot of trigonometric identity stuff, so it's going to be tough. Yeah, so we have the basics of all the identities. Now we have to move on to a bit more of a complex part of differentiation. Okay, now hyperbolic functions, you know that whenever you differentiate ddx of sine x, okay, so if you differentiated sine x, we'll be getting cos x. Okay, now that's a very simple one because we already knew how to do this. Okay, now if you differentiated cos x, let's write out every differentiate. ddx of cos x, that will be equal to, well, negative sine x. Okay, and we could go on and on. ddx, okay, yeah, so yeah, ddx of tan x. Okay, we could use the quotient rule, and yeah, we could do that, and we would be getting secant squared x. Okay, now most of these identities, they prove true for the same stuff as well. We can write ddx of sin x. Okay, this is true by the way. Sin x equals to differentiate of sin x equals to cos x, and the differentiate of cos x, and remember this one is a bit changed, we have to multiply by -1, so this minus is actually, now finally whenever you differentiate cos x, you get the same as sin x. Basically this is reversing it. Okay, if you differentiate this and you differentiate again, you get it back, same thing, no magnitude change, no sign change, nothing, it's the same. This however remains the same, so differentiating tanh of x gives you the sec squared of x. That's what you're gonna get. And yeah, it's a really easy identity to use. Now when you're going back to inverse functions, we know, well, let me erase that for you. Now we could just, you know, reverse. Okay, whenever you have to find the integral of sec squared x, you could just go back and find tanh x. Integral of this gives you this, and this is this, and goes on and on. Okay, this is the very easy part. Now moving on, we do have like a new concept introduced, and that's inverse functions. Okay, we know inverse functions, and we know what they are, we know their identities. For example, this is the identity for sin inverse of x. Okay, but if you differentiated an inverse function like this, if you differentiated an inverse function, you're going to be getting 1 over root 1 plus x squared. Okay, this is the result. Now how did we get this result? I'm going to show you for one, you can do it for the remaining. I will get to it in a minute. So ddx of cos inverse of x equals to 1 over, now this is also a root, x squared minus 1, and d dx of tanh inverse of x equals to 1 over 1 minus x squared, and that is it. Okay, now proceeding with it, I would give a much more of a, if I wanted more detail, actually I would prefer this sine inverse of x over a. Okay, sine inverse of x over a. If you differentiated this, okay, if you differentiated this, you'd be getting based on the mf19, you'd be getting 1 over root a squared plus x squared. Okay, and if you differentiated cos inverse, okay, of x over a, this time it's going to be a slight change. You're going to be getting 1 over x squared minus a squared. Okay, so it's essentially a equals to 1 for both cases, but this is a much more of a comprehensive guide, I guess. I think that's the best way I could say it. But yeah, this is much more comprehensive in that sense. Okay, now this is the basic of differentiation. Now why does this happen? Why do we get 1 over 1 or 1 over root 1 plus x squared? I mean, see, during exam day you're going to be given integrals and not differential equations, so you should know why it works. Let's look for the example of sine inverse of x equals to d dx of this equals to 1 over, let's prove the identity. I think that this is the, yeah, 1 plus x squared. Okay, so firstly I would use substitution. This right here, let's take it as u equals to sine inverse of x. So that means sine u equals to x. Okay, now differentiating with respect to x. Okay, or we could do it with respect to u. Actually, yeah, let's do it with respect to u. So d du of sine u equals to d du of x. Okay, now moving on, differentiating sine u should give you cos u, and differentiating x with respect to u will give you dx over du. Okay, now remember dx is what we're going to be using over here, so we need to replace dx with some sort of du. I'll get to that. So we isolate dx and we get dx equals to cos u times du. Now let's replace this entire thing over here. Yeah, so you can replace it over here. We'd be getting d over cos u du times, now sine inverse of x is u, so we have u over here. Okay, because we did substitute that, and we're basically differentiating this, right? Now here's the deal. Wait, yeah, so now we're going to just do a little bit of an isolation. So d over du times u over cos u, like that. And then using trigonometric identities you can move on, try out how to solve this. It's really smooth sailing from here, because now it's just the basics. So but yeah, so differentiating from this will lead to this result over here. One core thing that you could use is cos x, okay, cos squared x minus, sorry, cos squared x minus sine squared x equals to 1, and so that means that sine squared x equals to cos squared x minus 1. Okay, and that means sine x equals to root of cos squared x minus 1. Okay, these are part of the results that you're going to have to use. And same thing over here, you can replace cos x as root of 1 plus sine squared. Okay, you could replace it. You get sine squared x, and we know this is basically u. No, this is not u. Sine squared u. Okay, we're going to use u over here. So yeah, this is just root 1 plus u squared. So that's where you get that from. And then differentiating it from here, it's just real easy, and you'd be getting something along these lines. Yeah, you'd be able to differentiate and go along with it. Okay, now moving on, that was just the differentiating of it and why it works in some cases. Now for hyperbolics, these are the fundamentals that you're going to have to know. A few other stuff would be to preferably, whenever you're given to integrate something, okay, remember, if you're integrating sine x, okay, now remember, since it's written in terms of exponentials, it's going to be a bit funky. Now if you want to prove why that works, why this is equal to cos x, we could just simply split it as e to the power of x negative x divided by 2. Now integrating this is the same as 1 over 2 times the integral of e to the power of x minus 1 over 2 integral of e to the power of negative x, and yeah, going with respect to dx, obviously, with respect to x. And we could go along and we could do 1 over 2 e to the power of x. Simplifying this, we could do this, and yeah, it's just we would be getting minus times minus 1 by 2 e to the power of negative x. Now when we sum up 1 by 2 e to the power of x plus 1 by 2 e to the power of minus x, we'd essentially be getting e to the power of x plus e to the power of minus x over 2. And yeah, that's just it. So that's what you call cos x. Proving out using exponentials is the best way you can solve any kind of integration differentiation question. But that was just the fundamentals of hyperbolics. Yeah, with that being said, I think hyperbolics is one of the easier chapters, and is definitely a place that you won't be able to falter. Okay, so yeah, with that said, just a little bit more practice and I'm sure you guys will be able to ace any and every question given. So yeah, this has been a level up. Hope you've enjoyed this video. Thanks for watching, and I'll see you until next time.